Hello everyone. My name is Maishwari of Gnanasegaran and my metric number is 233-021-3955. Welcome to today's presentations where we explore the cutting edge research project titled Wavelet Based Features and Generative Adversarial Networks GANs for Image Forgery Detection and Localization. Within the broader context of image forensics, this project draws inspiration from the research article CNN based copy morphology detection using rotation invariant wavelet feature. As we leverage advanced techniques like wavelet based features and generative adversarial networks to enhance image forgery detection and localization. Image, Images plays a pivotal role in providing crucial evidence to elucidate events. However, the proliferation of diverse image editing tools has made image manipulation easily accessible, raising concerns about the authenticity of visual content. This is particularly concerning as a manipulated images, when exploited for malicious purposes, can have detrimental effects on society. The emergence of this issue underscores the need to reliably determine the authenticity of images, a task that has become increasingly challenging due to the difficulty of human eyes in detecting forged images. To address this challenge, it is imperative to develop robust image forgery detection methods. Numerous studies have been dedicated to exploring techniques for detecting various forms of image forgeries. One prevalent method involves copy forgery (CMF), where a portion of an image is duplicated from one section and pasted elsewhere within the same image. This process allows for image manipulation to either conceal or alter the original meaning of underscoring the importance of advancing our capabilities in detecting such manipulation. Uh, in this section, we delve into the realm of key point based copy morphology detection (CMFD) algorithms with a spotlight on the widely used scale invariant feature transform (SIFT). Moreover, the exciting developments explored in machine learning based CMFD showcasing the effectiveness of convolutional neural networks CNNs in detecting copy moved objects. In this research article, our focus then shifts to the proposed CMFD networks featuring four integral modules such rotation invariant feature, CNN based feature extraction, correlation and mask decoder. Notably, our network demonstrates the robustness in CMFD by leveraging the stationary wavelet transform SWT for rotation invariant features, utilizing low frequency and high frequency channels in the wavelet domain instead of convolutional RGB channels as input for the CNN module. The intricacies of the block-based approach explored in copymorph forgery detection methodology. The initial phase involves the division and segmentation of the image into blocks utilizing methods such as overlapping squares, non-overlapping squares, or circular blocks. To distinguish between the copied source region and the pasted target region, image segmentation techniques are employed. The next critical step is feature extraction, where features must exhibit invariance against scale and rotation, and resilience against various post processing steps. Transform based methods encompassing polar cosine, Fourier Mellin, polar complex exponential, Fourier, discrete cosine, and various wavelet transforms are commonly utilized in this process. Following this, the feature matching phase determines a candidate pair of the original and copied move parts. Employing sorting, hashing processes, and dimension reduction techniques in the searching methods. Similarity metrics including Euclidean, Manhattan, and Hamming distances play a crucial role in evaluating the similarity between features. The final step in this comprehensive approach is localization, where the detection output is visually presented as a binary image, highlighting the detected copy move regions and their corresponding authentic image paths. As we can see here, the figure 1 depicts the typical example of copy move forgery CMF, where determining the CMF um, using the naked eyes is difficult. Therefore, Therefore, the development of a reliable CMF detection (CMFD) method has become an important issue. In general, the copied part of the image is usually scaled or rotated before move process. Visual inspection alone cannot really verify the authenticity of the image. Hence, the aim of CMFD is to accurately detect or localize the copy move area, even if various operations, including scale and rotation, are applied before the image is manipulated. In this section, we will delve into the sophisticated key point based method within copy move forgery detection (CMFD) methodology. A focal point is the SIFT scale invariant feature transform key point extraction method, renowned for its robustness against scaling, rotation, and occlusion, rendering it highly suitable for CMFD applications. The, subs- the subsequent key point descriptor generation process involves SIFT generating scale and rotation invariant key points using a scale space representation through an image pyramid, each represented by a 128-dimensional descriptor. The matching process follows where key point descriptors are compared, addressing the common occurrence of false matching. To tackle this issue, various clustering algorithms such as J-lineage, distance-based, and hierarchical clustering are employed. This section presentation will also shed light on false matching removal techniques, emphasizing the frequent application of the random sample consensus algorithm, either independently or in conjunction with other methods. Next, in this section, the methodology of machine learning based approaches in copymorph forgery detection (CMFD) were delved. Recent strides in machine learning have notably influenced image processing and computer vision tasks, propelling the rise of breakthrough performance in CMFD methods. Notable approaches such as Bund et al. Proposed that combined CNN and LSTM method, and Liu et al. Introduced a CNN with a segmentation-based key-point distribution strategy, and Wu et al.'s proposed the BusterNet highlighted the diversity in techniques. This video explores on challenges and innovation of the research article, including high computational costs and accurate region localization difficulties. Zhang et al.'s dense inception net and Zhu et al.'s adaptive attention and residual refinement network showcase advancements with considerations for potential increases in training parameters and computational costs. Recent development In this recent development by Chen et al., Barney et al., and Liu et al. Highlight ongoing progress while acknowledging the significant impact of post-processing on forgery detection performance, as, as emphasized by Liu et al. Next, we delve into the proposed network in this research article. The proposed network for copymorph forgery detection (CMFD) comprises four modules, such as rotation invariant module, feature extraction module, correlation module, mask decoder module, and localization. Let's dive through one by one. In the rotation invariant module, the root mean squared energy using high frequency wavelet coefficients are used to provide rotation invariant features to the feature extraction module. The conventional CNN can obtain the scale invariant characteristics by viewing images on various scales because the convolutional operation is performed using filters. Then, the proposed wavelet-based input contains rotation invariance and a large field of view is feature extraction module. Hence, the basic VGG16 structure is sufficient to extract features for CMFD. VGG16 that is used in this paper contains four standard convolution groups, such are the convolutional layers 3 times 3, the number of kernels in the four groups such are 64, 1 to 8, 256 and 512. Each standard of convolution possesses a ReLU activation functions, and each group is followed by a max pooling layer. Next, the architecture of the proposed CMFT network is a correlation module where the feature extraction module based on VGG16 generates 16 times 16 feature patches that amount to 512. To obtain the potential copied and moved patch pairs, the all-to-all feature similarity score is computed using the correlation module. The correlation module comprises self-correlation, percentile pooling, and batch normalization blocks. After that, the mask decoder module generate a 16 times 16 feature block whose resolution is lower than that of the input image. Moving to the last stage of localization, in order to develop a pixel level localization map, a single standard convolutional layer is generated followed by a sigmoid activation function is utilized uh, in this proposed network of the CMFT copy move forgery detection. In this research article, they have utilized the four public datasets with ground truths, namely Comofort, Mike F2000, D, and coverage. These four datasets is listed in table 2. The dataset of Comoport has a corresponding 5000 tempered image with a resolution of 512 times with 512. The Mike F2000 dataset has 700 tempered images with resolution of 2048 times 1536. D dataset has 970 tempered image with resolution of 700 times with 1000. Meanwhile, the coverage dataset having 100 tempered images with resolution of 400 times 486 that is reliable that are reliable for experimentation purposes. These images are divided into three categories, namely training, validation, and test at a ratio of 7, 1.5, 1.5 respectively. The performance evaluation measures were evaluated by defining the three measures of pixel at the pixel level, such are TP, FP, and FN. The three measures are the numbers of correctly detected as forged and falsely missed forged pixels, respectively. Precision denotes the probability that a detected forgery is truly forged. It is expressed as precision equals to Tp divided by Tp plus Fp. Recall denotes the probability that a forgery is detected, which is expressed as recall equals to Tp divided by Tp plus Fn. And the overall detection performance, namely F measure, is defined by the harmonic mean of precision and recall as follows, that is F equals to 2 times precision times recall divided by precision plus recall. This is the formula that were implemented in this research article. Next is the simulation results. In these simulation results, the performance of the proposed CMFD network were evaluated based on the three methods, based on the three SIFT based algorithms method, which is compared on the SIFT plus FM, feature matching, SIFT plus and, and adaptive segmentation, SIFT reduced local binary pattern, SIFT plus RLBP. Further, two machine learning based networks are selected for comparison with the proposed network, BusterNet, and the serialized network, SENet. The the comparison of the computational performance are shown in the table 3, 4, and 5. In the running time, in order to compare the computational cost, the execution times for all CMFD methods and the number of parameters for CNN-based methods were implemented, and the execution time was average over 20 operations. Table 3 shows the execution time for the test process and the number of parameters of CNN-based methods. The proposed network achieves the fastest average testing time, and SENet has the second fastest testing times. Next, move on to the detection results, where the test images were divided into two groups of forged image without and with the rotation attacked in order to evaluate the effect of the proportion rotation invariant wavelet energy feature. Table 4 lists the three evaluation measures for forged images without a rotation attacked. As shown, the proposed method achieves the best performance. The SIFT based algorithms such as SIFT plus FM and SIFT plus segmentation learning based method include the proposed method identify even some of the copied or moved areas. Table 5 lists the three evaluation measures for copied move images with a rotation attacked. In general, the CMFT performance is degraded when a rotation attack is applied during the move process. As shown in Table 5, the F-value of all methods is reduced compared to that when no rotation attack occurs as listed in Table 4. The figure 9 here presents the comparison of the forgery detection results of selected test images without a rotation attack. This figure 9 shows that the SIFT based CMFT methods often fail to detect the forged regions. In contrast, the machine learning based methods, including the proposed method, identify even some of the copied or moved areas. The proposed network detects the proposed network detects both copied and moved regions with few failures. In contrast, this is the figure 10 that shows comparison of the forgery detection results of selected test images with a rotation attack. In this figure, in this figure 10, the proposed method adequately detects the forged region despite the small errors, whereas other method fail to localize the forged regions of most of the time. As a conclusion, this research article proposed a novel copy move detection network using CNN neural networks. The four blocks to localize the copy move regions were developed, and a wavelet-based rotational invariant module used to the high-frequency stationary wavelet subbands was proposed. This root mean squared energy achieved a robust performance against rotation attacks. Not just that, the conventional VGG16 structure was used as the main feature extraction module. The correlation module was adapted to generate potential copied and moved patch pairs, and the feature similarity score was computed using this module. Finally, in this research article, the simplified mask decoder module is implemented to reduce the reinforcement of small spots using bilinear interpolation. Overall, the proposed method was compared with existing CMF localization algorithms. The simulation results demonstrated the proposed network had almost no difference in F-measure values between the forged image with rotation and the tempered image with scaling, whereas the existing CNN-based methods showed a difference of the existing of CNN-based more than 10%. As for the synthetic dataset, the proposed method outperformed state-of-the-art approaches by 12% in terms of the F-measures. Hence, this research article aligns with my project entitled Wavelet-Based Features of the wavelet-based features and generative adversarial networks (GANs) for image forgery detection and localization. Thank you.